All right, so once again, we're getting into rates of change, and part of advanced function is for every function, type of function that we look at, whether it's a polynomial or rational function or the ones we'll see in the future here, we're going to find rates of change. Now, kind of tying back into what we did before, where I'm looking for the average rate of change. Now, when you're finding the average rate of change, that essentially just means you are finding the slope. So our average rate of change, in this case, we are looking at the average rate of change between -5 and -3. And so in terms of our x1, x2 values, the farthest to the left is our x1, and our farthest to the right is x2. And so for this function, what we will be looking at is substituting f of -3 minus, this is my y2 minus y1 going on here, f of -5. And of course, all over x2 minus x1, which in this case would be -3 minus, minus 5, two negatives there. Now, what I like to do to keep things separate is I like to figure stuff out on the side here. So f of -3, let's see here. I plug a -3 in for x into our function there above, and I get 1/3. So which as a decimal would be 0.33. If I put in f of -5, see on the bottom there, I'd have -5 plus 6, which would be a positive, just a positive 1. So 1 divided by 1 is 1. All right, and so I can substitute into my equation here for the average rate of change, again, just finding the slope, where I'd have 0.33, subtract 1. And then on the bottom here, I would have, let's see, -3 minus -5, which means +5, so it would be a 2. And so 0.33 minus 1 is -0.67 divided by 2. And I guess rounded to 2 decimal places here, I get -0.34. So again, that's finding the average rate of change. But here's what we're looking for. We're going to be looking for, more appropriately, is the instantaneous rate of change. All right, now in our first unit, that's where we use limits. But again, we'll get into that more so when we get to calculus, but we're all about the estimating right now. And we have our x value at 4. And so again, this is where we're combining that limit formula and our slope formula together. And so what we're going to be finding here is our estimate of our instantaneous rate of change, hence the I instead of the A. And we'll be doing that at x equals 4. All right, and so this is where we're going to be, again, looking at our slope formula. So we'll be looking at f of 4, but again, adding just a little bit. So we're going to go with 1/100th, f of 4.01. Again, that little 0.01 refers to that h value that approaches 0. But in this case, we're just going to say it's really, really small. We're actually going to put a number in there. Again, subtract f of 4 divided by, again, x2 minus x1, which is our 4.01 minus 4. So again, when I'm figuring these things out, I'm going to plug in over here. So I'm going to find my f of 4.01. And so on the denominator there, I'm going to take 4.01. I'm going to subtract 6, and then I'm going to go 3 divided by that number. And I end up with -1.51. All right, now I still got to find my f of 4. So on the bottom there, I'd have a 4 minus 6, which is a -2. And so 3 divided by -2 is going to be -1.5. All right, so now I can find my instantaneous rate of change. I've got my -1.51 minus, I got a double negative again here because there's a minus sign in the equation, and there's a minus sign for this f of 4, which is, again, -1.5. And then if I have 4.01 minus 4, well, that's just 0.01. All right, let's see here. Do a little math on the top. Again, the double negative is going to give me a positive. And let's see here. Oh, I end up with negative 0.01 divided by 0.01. And so our instantaneous rate of change is just a -1. There we go. So again, using that whole idea of this 0.01 basically being substituted in as our limit as h approaches 0. But again, using our slope formula. All right, let's try something a little bit tougher, a little bit different. Little word problem. Example 3. The snowshoe hare population in a newly created conservation area can be predicted over the time model by that equation right there, where P represents the population size and T is the time in years since the opening of the conservation area. Estimate the instantaneous rate of change after 2 years. Include the units because we actually have a real life thing going on here. All right, so again, we're going to find the instantaneous rate of change. All right, and we're going to do that at x equals 2 years. So what our formula is going to look like, well, we got the P formula here, so I won't use F of, but we're going to use the P of 2 plus a little bit, so 2.01 years minus P of 2 divided by x2 minus x1, which in this case is going to be 2.01 minus 2. All right, so I have this huge equation over here, and so let me see here. P of 2. P of 2 first, the whole number. I'm going to get 50 plus. All right, so let's see on the top there. You get my calculator out here. I got 2 squared times 2,500. So 2 squared is 4 times 2,500. Should just be 10,000. It is. So I got a 10,000 on the top here. All right, put a 2 in the bottom. Well, that's going to be 4 plus 25 is 29. All right, and so let's see here. I take 10,000 divided by 29. Let's see here. And then plus 50. And I'm getting, let's see here, to 2 decimal places. Equals 394 into 2 decimal places, 0.83. That's P of 2. Okay, now I also have to do P of 2.01, which I already did. I'll be honest with you. I already did this one. And so I substituted 2.01 in for T there into my equation again. And this time I got 397.8 when I substituted in my equation. All right, now I can find my instantaneous rate of change. I got 2.01, which again, here is my 397.8. Subtract my 394.83. And let's see, 2.01 minus 2. Again, that's 0.01. All right, equals, let's see here, subtract those two. And I get 2.97 divided by 0.01. All right, now the final numerical value is 297. But this is a word problem. And again, what we're talking about here is the population of hares or rabbits, if you will, snowshoe hare. And this was with respect to time and years. And so what this means is, therefore, the hare population is, it's a positive number, is increasing at a rate of 297 hares per year after 2 years. So this is saying that the population is increasing. It's going up after 2 years by 297 hairs per year. And there we go. So there is a rate of change. Instantaneous rate of change, I should say. All right, just check chat, make sure there's no questions there. All right, so let's see. Let's try another one here. I think I got some real life examples here. I always love including science. So this is real, actually. So after you eat something that contains sugar, the pH or acidic level, for those of you taking chemistry right now, I know there's a bunch of you, in your mouth changes. This can be modeled by the function L of M is equal to that big equation there, where L is the pH level and M is the number of minutes that have elapsed since eating. So estimate the rate of change at 3 minutes to 3 decimal places. Include your units. So there again, we're finding our instantaneous rate of change at 3 minutes. So our instantaneous rate of change is equal to, and again, that is at I guess we call it M this time, at M equals 3. All right, and so we have our L level. I guess L stands for level here. And so we're going to do 3 in a little bit. So L of 3.01 for a little bit past 3 minutes. Subtract L of 3. All over, again, our x2 minus x1, or m2 minus m1, I guess I should say in this case. So 3.01, subtract 3. All right, so let's see here. Over on the side here, I'm going to figure out L of 3.01. All right, so let's see. I substitute in at the top there. I got, let's see, negative 20.04. 20.04 times my 3.01. What do I get here? Negative 61.4. There we go. Then on the bottom, and I can't forget this plus 6.5 over here. In the bottom, I got m squared plus 36. All right, so I take my 3.01, square it, add 36. What do we get here? 45.06. Okay. Now, let's see, do a little bit of math here. I get my negative 61.4 divided by my 45.06. All right, then I get negative 1 point something, and then I add 6.5. I'm getting, and it says the 3 decimal places, so there must be a reason for that. So I go 5.137 is what I ended up with. All right, just doing my calculations. Now I'm going to cheat a little bit here and tell you that I already did pump in L of 3. It was a little bit easier, obviously, because it's a whole number. And I got 5.14. All right, so now to find my instantaneous rate of change. So we got, let's see here, 5.137 minus my 5.14. And again, I'm going to divide that by, let's see here, 3.01 minus 3, 0.01. All right, and now I do some subtraction, then divide, and I actually get negative 0.3. But again, this is a word problem. Need to actually explain what this means. And well, therefore, what are we talking about? The pH level. The pH level is, now that's a negative number. So it is decreasing at a rate of 0.3 pH levels per minute, because that's what our time's in, per minute, after 3 minutes, which is the X value we checked it at. Well, the pH level is going down. I haven't taken chemistry in a while, so I'm not sure if that means more acidic or less acidic. Not sure how that goes. All right. Again, that's a real life formula. That's for real. I got that. Let's try another one, which is real. This comes in my physics background here. Some of you have already taken my physics class or going to. Example 5. As you get farther from Earth's surface, gravity has less effect on you. That's true. For this reason, you actually weigh less at higher altitudes. Because, yeah. An astronaut who weighs 85 kilograms can use the function W, the weight function, is equal to 2 times 85 divided by h plus 2 to find their weight in kilograms at height h in meters in thousands. All right, so thousands of meters above sea level, above the Earth's surface. Here we go. That's a wordy question, but estimate the instantaneous rate of change of the astronaut's weight when they are 5,000 meters above sea level. Include units. So again, we're looking at the instantaneous rate of change. All right, equals. Now, this is 5,000 meters above sea level, and our height actually is in thousands. So we'll be checking this instantaneous rate of change out at x equals 5, or sorry, h equals 5, because we got 5,000 meters we're looking at it. So we want to know what our weight is in kilograms here, which, well, we'll talk about that in physics. All right, so here's what we're looking for, is that I'm going to find our function. What do we got? Our W function at 5, a height of 5,000, 0.01, just a little bit higher, minus, again, our weight function at 5. All over, again, our H2 minus H1, I guess, if you will, in this case. So 5 minus 5, or 5.01 minus 5. Now I just go over here, and let's see here. I need W of 5.01. Let's see here. Oh, that's an easy one. I just pop, I got 7.01 in the denominator there. So 2 times 85. And then divided by 7.01. And I get 24.25. I can also find W of 5. And well, that just means I take that 2 times 85 and then divide by 7, which I end up with is 24.29. All right, so substituting our values in. So I get my 24.25. Take a 24.29. And let's see here. Down here, well, I'm going to have a 0.01. All right, so I do some math there. I take my 24.25, subtract my 24.29, and then divide it by 0.01, and I get minus 4. Okay, so again, what does that mean? Our weight is in kilograms. Our meters are each one is 1,000. So that is saying this is therefore the weight, or the, I guess, the astronauts weight. How do I spell knots here? Astronauts. There it is up there. Astronauts weight is the negative sign again, so that means decreasing at a rate of 4 kilograms per, not 1 meter, but this is in thousands of meters, so per 1,000 meters at 5,000 meters above sea level. There we go. So anytime you have a negative rate of change, it's decreasing. If you have a positive, it's increasing. And again, here's one where the units were just a little bit different.